එහෙනවද? එහෙනව නේද?
සහනෝ
පොඩි technical failure එකක් university එකේ power ගියා. Right. So I was talking about the avalanche effect. So what's happening in Senate nowadays? You have this high dope concentration. So if you have one electron moving in the opposite direction, it can hit other electrons and release them from their bonds as well. So gradually, your single electron become 1, 2, 4, 8 like that, and you get a large number of current flowing through the diode at a lower reverse bias voltage. So that is why you have a lower breakdown voltage for a Zener diode, and that's how you change the potential barrier. By changing the concentration, you can determine when you will have this particular effect. So based on that, you can have a current flowing through the diode in the reverse bias mode without damaging the diode. Right? So that is the structural difference in the Zener diode. Right. Anything else?
So excuse me.
Yes. And
It's okay, Ashan, you ask, then I'll ask again.
ටෙක්ස්බුක් එකේ අර ෆුල් වේව් රෙට්‍රිෆය එකේ තව කොටස් දෙකක් තියෙනවා සෙන්ට්‍රි ටැප් කියල එකකුයි අර බ්‍රිජ් රෙට්‍රිෆය කියල එක මේ ඒ දෙකේ ඩිෆරන්ස එක චුට්ටක් කියන්න පුළන්ද අර අයිඩිය එකක් දෙන්න පුලන් සයක ගෙනගෙන නෑ කලින්මිට
ඔකට සෙන්ටර් ටැප් එක කරලා තිබුණේ නැද්ද?
නෑස
Right. Now what's happening is there are different types of transformers. You might have learned about transformers that the usual transformers have 2 input wires and 2 output wires. Right. Transformers basically made from so it's basically a collection of coils. Right? You have one here. You have some kind of medium, probably a soft iron core or something. And then you have something like this. So depending on the number of windings, the ratio of number of windings in the primary and secondary, we call it primary and secondary, your output voltage can either be less than or equal than or greater than the input voltage. I think that you have learned. So what's happening in the center tap is somewhere in the middle of this coil, you tap it and get another wire out. So this half work as one transformer and this half work as another transformer. But if you look carefully, this one has in one way of winding, and respect to this, this has the other way of winding, right? So you can think of it like this. If you're applying, let's say getting 12 volts, you might get, let's say for the time being, assume this is positive and this is negative minus 12, the center point will be 0. Of course, you won't get positive or negative, you will get the AC one. But the thing is, this will always remain the 0. Only these two wires will start changing the voltage. You can assume this as the ground line, the 0 voltage. With respect to this, this will go up and this will go down. Then this will go up and this will become down. Right? So if you have something like this, you will get a waveform like this, and this will have the opposite waveform. So when you have a line connected to the center of the secondary coil, that is known as a center tap transformer. There can be other places as well. You can have multiple taps, those are called multi-tap, but for a center tap, you have something like this. So the advantage is in the center tap one, you get a 0 line like this. With respect to this, the phase difference between these two terms will be opposite. If this is positive, this will become negative. If this is negative, this will become positive. So they will always have the opposing phases. So this kind of design is known as the center tap transformer design. Is that clear?
yes sir, it is
Okay, so that is the difference in the center tap transformer and a normal transformer. Let's go back to our PowerPoint. Anything else you want to ask?
So excuse me.
Oh, Ahan.
So then මේ අපි normal diode එකක් ගත්තොත් එimhe reverse bias වෙනකොට current එක 0 නේ.
Oh,
එතකොට voltage across the diode is equal to the applied voltage.
oh, ඒ කියන්නේ
Normally
diode එක
survey-
දෙපැත්තේ තියෙන එක. හොඳේ වෙන කොහෙවත් තියෙන voltage එකනේ diode එක reverse bias කරලා පහක් දුන්නොත් diode එක දෙපැත්තේ පහ හිටිනවා.
ඔව් සර්. එතකොට දැන් මේ textbook එකේ 71 page එකේ තියෙනවා unlike in a normal diode the zener will not get destroyed by the breakdown and process is reversible කියලා.
Oh.
ඒ කියන්නේ සර් දැන් zener එකට වඩා දැන් normal diode එක ගත්තොත් කොහොමත් මේ current එක 0 නේ. කියන්නේ current එක 0 උනත් ඒ කියන්නේ ඒක destroy වෙනවද? මේ කියන්නේ reverse bias වෙනකොට. current එක 0 නම් ඒක through එතකොට
නෑ මෙහෙමයි. normal diode එකක current එක ඇතුලෙන් ගියොත් reverse bias අවස්ථාවේදී ඒ කියන්නේ diode එකට වැඩේ වෙලා ඉවරයි. හැමතිස්සෙම breakdown වෙන්නේ නැහැ. ඒ කියන්නේ අපි හිතමු diode එකක් create කරලා තියෙනවා කියලා 100 volt reverse bias breakdown එකකට. එතකොට 5 volt 10 volt 20 volt 90 volt වෙනකන් දුන්නත් ප්‍රශ්නයක් වෙන්නේ නැහැ. අපි හිතමුක වැරදිලා ගහපු කියලා 230 line එකට. දැන් මොකද වෙන්නේ? අර 100 volt rate කරපු එක 230 ගහපු ගමන් diode එක pitch වෙනවා. pitch වුණාට පස්සේ diode එක නිකම්ම wire කැරලක් විතරයි. එතකොට current එක යනවා. ඒක රිවර්සිබල් නෑ. diode එක current යන wire එකක් වුණාට පස්සේ ආයි diode එකට හරවන්න බෑ. ඒක රිවර්සිබල් නෑ. zener diode එකේ current එක conduct කරන තත්ත්වයට ආවත් diode එක wire එකක් වෙන්නේ නෑ. ආයි ඒ apply voltage එක අයින් කරාම diode එකකට තමයි තියෙන්නේ. ආයි ඒක damage වෙලා නෑ. ඒකයි රිවර්සිබල් කියන්නේ. අරක කියන්නේ කලින් පිච්චිලා කළු වෙලා අඟුරු වෙලා ගියා. ඒක රිවර්සිබල් නෑ. zener diode එකේ current එක conduct කළත් ඒකේ තියෙන rate එකක් තියෙනවා. maximum voltage එකක් තියෙනවා. ඒක ඇතුළේදී current එක conduct කළා ප්‍රශ්නයක් නෑ. ආපහු යන්න පුළුවන්.
ඕකේ සර්. කියන්නේ ඒක ස්පෙෂල් කේස් එකක් නේද? එහෙම destroy වෙනවා කියන එක. අර ඒ කියන්නේ ඒක increase වෙලා ගිහින් එහෙම වෙන එකක් නේද?
ස්පෙෂල් කේස් එක වෙන්නේ zener එක.
ඔව්.
එන්නේ කරන අනිත් ඔක්කොම ටික තමයි destroy වෙන්නේ. zener එක තමයි ස්පෙෂල් කේස් එක. හොඳේ? destroy වෙන එක normal කේස් එක. destroy නොවි තියෙන එකම diode එක තමයි zener එක. ඒකට ස්පෙෂල් කේස් එක zener එකට තියාගන්න. generally වෙන්නේ destroy වෙන එක මේ reverse bias එකේ current එකක් යවන්න හැදුවොත්. හැදුවොත් කියන්නේ ගියොත් පොඩි ගාණක් නෙමෙයි. ඒකේ breakdown voltage එක පැන්නොත් destroy වෙනවා.
ඕකේ සර්. රයිට්.
ඔව් හැමතිස්සෙම මේ reverse bias කරාම diode pitch වෙනවා කියලා හිතන්න එපා. ඒකේ ඒ සීමාව නිශ්චිත data sheet එකේ තියෙනවා. මේකයි PIV මේකයි maximum current අනම්මනම් ටික. ඒ ටික පැන්නොත් මේ diode එක damage වෙනවා. right?
excuse me sir.
yes.
sir අපි zener diode එක forward bias එකේ තිබ්බොත් current එක කොයි වගේ වෙනවද?
අනිත් diode වගේම තමයි ඉතින්.
කියන්නේ ideal නම් zener diode එක forward bias නම් maximum current එකක් flow වෙනවද?
ideal නම් කියන්නේ මෙහෙමයි. forward bias එකේදී කොහොමද zener diode එකක් නිකන් diode එකක් වගේම තමයි. ඒකේ potential barrier එකක් තියෙනවා. මට මතක නැහැ කොහොමද ඒක වෙනස් වෙන්නේ කියලා. අපි හිතමු 0.7 කියලා. ඒතකොට සාමාන්‍ය diode එකක් වගේ තමයි. 0.7 වෙනකන් current එක යන්නේ. 0.7 ඊට පස්සේ current එක යනවා. reverse bias එකේදී විතරයි වෙනස. අනක නිකම්ම diode එකක් වගේම තමයි. සමහරට අර potential barrier එකේ වෙනසක් තියෙන්න පුළුවන් 0.7 නැතු වෙන ගානකට. නමුත් behavior එකේ වෙනසක් නැහැ.
okay sir, thank you.
Right, since most of students are here, let me give the two notices I wanted to give. One thing is I was getting so many requests to make practical exemptions. I make the deadline extended and we discussed with the head of the department. So you can apply it up to 4 years, 5 years in the previous, if you have done practicals in the previous 5 years, you can apply for the exemptions. There's a Google form, fill it. You have to fill it before the 14th because otherwise I won't be able to calculate the eligibility marks. But I recommend you to do the practicals because that will refresh your knowledge. But for some reason, or if you feel too lazy, then I can't force you. Then you can apply for the exemption. But if you are able to attend, please attend the practicals. That will be good for you. There will be 2 new practical groups. 2 means after the final exam, we put 2 practical groups. So please register for one of these groups. Again, we originally intend to have 1 group because there are so many CAT exams and everything, we couldn't find a slot. But there were requests from many people who are working to put a group for the weekend. So we put a weekend group as well. So if you can attend the weekday group, please attend that one and keep the weekend one for the people who are not able to come to the weekday group, right? So that's the first notice. You can apply for the extent for the practicals. If you have already filled the Google form, don't need to apply again. I already have that. But if you are a new person who want to apply for the exemption, please do it before the 14th. And since this is the COVID period, they have made a decision to extend it for the last 5 years. Usually I don't do it. Usually all the departments keep it to maximum of 1 year, but due to COVID and all these things, we decided to do it for 5 years. And justifications, if you can provide, that's good. Even if you don't put the justification and just ask the request, head that instruct on me to do it, so I will give you the exemption. But if you can come, I recommend you come into it because it will help you refresh your memory. Whether it's coming or not, it's up to you. That's the first one. Second one is the examination. CAT 1 will be held online. It will be a MCQ short answer type question. So that means either you have to select true, false, select the correct answer, that sort of thing, or you have to do short calculations. So short answer means you don't have to write the steps. You only have a place to write the final answer. Maybe Ohm's law, what's the current going through this diode or something like that. So you have to put it there. So that's the format we are going to have. And I originally intend to have going up to the transistor, that means session 8. So we are still at session 6. So I have to cover 2 sessions. I will try to give the basics of transistors today within the next 15 minutes. And you can go through the previous recordings as well, because I want to go up to the transistor. So 6, so the BJTs and session 8, which is some transistor calculation. So be prepared up to that point, and those will be the sessions coming to the CAT 1. Anything you want to ask regarding that?
Excuse me, sir.
Yes.
Sir, අපේ session 7 වෙන්නේ BJT transistors.
Oh, හත කොහොමද වෙනවා?
Session 8 as a field effect transistors. ඒක එනවා sir.
ෆෙට් එකේ කැල්කියුලේෂන් නම් මුකුත් ඕගලන්ට කරලා නැහැ. ඉතින් ෆෙට් එක ඇත්තටම ඕගලන්ට ආවොත් පොඩ්ඩක් මේ මොකද ෆෙට් එක කියලා බලා ගන්න විතරයි තියෙන්නේ. මට හිතෙනවා ෆෙට් එක ඇත්තට ලේසි වෙයි කියලා BJT එකට වඩා. ඕගලන්ට ගොඩාක් කම්මැලි නම් ඉතින් අපි 7න් නවත්තමු. හැබැයි මට හිතෙන්නේ 8 ලේසි කියලා.
Sir, ෆෙට් එක ඒ MOSFET JFET sir පොඩ්ඩක් කරන්න ඕනේ sir. මේ මොකද අපිට A levels වලටත් ඒක ඒ part එක හරියට cover වෙන්නේ නැහැ.
Right, then we limit to session 7. In the learn OSL, I think I have put up to session 8, so I will change it to session 7. Okay, so we'll go up to the BJTs. Right, let me quickly recap what we are going to cover with the BJTs, so you can get an idea what we are going to do. The transistor is a 3-terminal element. It is the basic of most of the modern day electronics. What about the new one? Okay, there's a question. Thing is, after the 2 practicals, we will be doing, excuse me for me. Right, so we were talking about the Viva sessions. So after the 2 initial groups, we will have the Viva sessions as well. So the idea is, I think there's one group we did not take Viva because we had to close it or something. I think university closed or the final exam came or something. So all the people who were not able to attend those Viva, we will take in the upcoming Viva sessions. We have not finalized dates yet. They will probably come after the practical, new practical dates, right? Usually we give about a week after conducting the practical to do the report, and then we will have the Viva. So those who did not report, who did not attend the Viva earlier for some reason, they can join that one as well. And we will have Viva for the new two groups as well. Anything else? So that's the question I think I answered for that one. Okay, so we'll come back to the lesson. So transistors are a type of elements known as active elements. Do you know what is an active element? Active element එක කියන්නේ මොකද්ද? Diodes and resistors, all these things are known as a passive elements. Do anyone know what's an active element? Active element එක කියන්නේ මොකද්ද? Okay, now remember, in the electronics, we are working about or talking about information and knowledge and digital signals and things like that. If you can amplify the energy of a signal, that is an active element. Amplify the energy, power, voltage, right? Not just the current, not just the voltage, the total power. If you can amplify it, that's an active element. If you can't amplify it, that's a passive element. So is a diode active element or not? Diode active එකක්ද නැද්ද?
Is active element.
No, that is not active element because you can't amplify power. Transistor is an active element.
Okay, sir. Transistors.
Yeah, transistor is an active element. Diode, capacitors, other things are not active. What about transformer?
It is a passive element.
It is a passive. You can increase either the voltage or the current, but not both. Now, when you remember, when I say the word power, that needs to come with both V and I. Remember, W is equal to VI, right? So transformer again is a passive element. It's not an active element. So let's look at the transistors. That's one of the main active elements that are used in electronics. Okay, so transistors come in two different flavors. You can categorize them in two different ways. One is known as the bipolar junction transistors, or in short, we call it as BJTs. BJTs again break into two different categories, NPN transistors and PNP transistors. So those will be the focal point of our this session, not next session, this session. And after that one, we are going to look at the field effect transistors. In short, we call it as FETs. FET will be the session coming after this one. Again, FETs are categorized into two different ones, JFET and the MOSFET. JFET stands for junction field effect transistors. MOSFET stands for metal oxide semiconductor field effect transistors. After that, you have a different categorization based on the way it works. You can categorize them either as depletion or the enhanced mode. Now for the JFET, you have only the depletion mode transistors. But for the MOSFET, you have both depletion and the enhancement mode transistors. And the last category is similar to the NPN and PNP channels in the BJT. So rather than having NPN or PNP, we have only a single channel. So we call them as either N channel or P channel. So all of the FETs can be categorized as either N channel or P channel FET transistors. So those are the main categorizations or classification of the transistors. Now let's look at our today's main topic, which is the BJT transistors. Now transistor has three leads or terminals. For a BJTs, we call them as collector, base, and emitter, right? So a transistor consists of either a N-type semiconductor sandwiched between two P-type semiconductors, or P between two N-type semiconductors. So whatever the thing that is in the middle is called the base. So in a PNP transistor, base is an N-type element, while in an NPN transistor, base is a P-type element. Now, if you look at the emitter and the collector, you can see they have the same type of semiconductors. They are same type. Either both of them are P or both of them are N. So you might be tempted to see, okay, they should be equal, but that is not the case. Emitter and collector might be the same type of extrinsic semiconductors, but there's a major difference. The difference is the doping concentration. Emitter is usually highly concentrated, while the collector is not. So it's not good idea to change the collector and emitter. They might be both P, but their concentrations are different. Therefore, that's why you have three different names. You have the emitter, you have the collector, and then you have the base. In certain cases, you can think of it like having two diodes connected together, but most of the time that is not a very good approximation, but sometimes you can think of it like that. So now you know the three terminals of the transistor: collector, base, emitter. Other than that, there are some standard notation regarding the transistors. For example, current going in or out from the collector is known as IC. So whenever you have the word current, when you are measuring the current, you use the letter capital I. So IC means collector current going through the collector. IB means current through the base. IE means current through the emitter. And whenever you have the word V, that stands for the volt, that will be the potential. There are two different notations for the potential. If you say something like VB, capital V, capital B, that means the base voltage. Base voltage. Now remember, voltage is a potential difference, so it needs to be measured with reference to some other point. So when you say VB or the base voltage, you are measuring it with respect to the ground. You are measuring it with respect to the ground. Right? So ground might be somewhere else in the circuit, but you are measuring the voltage with reference to the ground point. So when you say VC, you are measuring the collector voltage with reference to the ground. VE means measuring the emitter voltage with reference to the emitter. In certain cases, you don't want to measure everything with respect to the ground. You want to compare the voltages in different terminals. Let's say I want to measure the collector voltage with reference to the emitter voltage. I want to know the voltage difference between collector and emitter, not referring to some ground. In that case, we use two letters in the subscript. We use VCE. VCE, that means collector voltage with reference to the emitter. Similarly, we can say VBE. That means base voltage with reference to the emitter. Right? So we use that terminology in transistor calculations and circuits and everything. So even in the exam, I might directly say calculate IC, calculate IB, calculate VCE. Then you should know what VCE is, right? I should not have to explain what is VCE. You have to know this. And sometimes, not sometimes, most of the time circuits will have resistors connected to these terminals, and they will have the same kind of notation. A resistor directly connected to the collector, usually named as RC. Resistor connected to the emitter will usually notated as RE, and similarly we will have RB. So that is about the labels and notations. Is it clear? පැහැදිලිද? The notation එක කිව්ව ගමන් දැන් මේක කොහෙද කියලා තේරෙන්න ඕනේ. පැහැදිලිද ඔයගලන්ට?
Yes, sir.
Okay. What is meant by IRC? IRC කියන්නේ මොකක්ද? chat එකට දාන්න බලන්න නැත්නම් කියන්න කවුරු හරි. What is the first word? I means, what are we measuring? I?
Current.
Current. RC? What is R? R means a resistor. Which resistor? C. C means collector. So that means current through the resistor connected to the collector terminal. There's a resistor connected to the collector. Current through that one is called the IRC. Right? Right. Now let's look at the transistor configuration modes. Now remember, in the transistor session, you have so many words. So what is a configuration mode? In the first lecture, I explained electronics is all about processing information and data. So that means you have some kind of input signal and you want to generate some kind of output signal. When you have an input or output, you need to have a closed circuit. That means you need to have at least two wires, right? If you have a speaker as the output, you need to have two wires to supply the current. If you are using a microphone, you need to have two wires coming out from the microphone, right? So inputs and output need to have two wires. Otherwise, the circuit is not completed. So two wires for the input, two wires for the output. In total, we need 4 connections. But our transistor has only 3 terminals. So if I want to use transistor to process information, I have to make a small adjustment. I have to use a certain terminal, one of the terminals common for the both input and output, right? So there will be a terminal or a pin common to the both input and output, right? So based on that, we have 3 transistor configuration modes. So in the first image, you can see this is my input, this is my output, and this terminal, this is connected to the input and it is also connected to the output, right? So this terminal is the base. So base is connected to the input and base is connected to the output. So this is a common base configuration. So signal comes from the base and the emitter, and output comes from the base and the collector, right? So in a way, you can say then input is the emitter and the output is the collector and base is the common one. That's again okay. In this case, what terminal will get the input? So the common one is, what is the common terminal for this circuit? Collector. Which terminal gets the input? If you neglect the common one, what is the input terminal?
Collector and base.
Yes, let's ignore the common one, okay? Then it will be the base. Output? Emitter. Similarly, here you have the input as the base, output as the collector, right? So based on that, we have 3 configurations known as common collector, common base, and common emitter. You can repeat the same thing for PNP, but the names is the same, right?
So excuse me.
Oh,
So in that last one, why the signal is it has a phase change, right?
Yes, very good. This one. I'll come to this one. So based on the way you have connect the transistor, the behavior changes. So one change you have already noted. This one goes upside down. There's a phase change. There are other changes. So let me show you this one. Okay. So this is the common base, common collector, and common emitter. This is the one you are referring to. Input-output phase relationship. In the common base one, there's no phase difference. Common collector, no. But for the common emitter, you have 180-degree phase difference. So when the input increases, output decreases. When the input decreases, output increases. They move in the opposite directions. So that is why you have the phase difference in it, right? In addition, you can look at the gains. So you can see if you have a common base, you have a high voltage gain, but the current gain and power gain is very low. Common emitter, you have a different scenario. And overall power gain, that means current and voltage gain together, is medium. Common emitter is the one that has the highest power gain because it amplifies both current and the voltage. So that is why in most cases, you will see this common emitter configuration is used. So it has a higher gain. However, it has this particular flow. It's not a flow. The problem is it will change the phase of your input signal. But other than that, you have a very good amplification for this configuration. Right. Now, before I go to the next one, I need to ask a question. Now, originally, I was allocated from 1 to 3. So now it's, I think, around 3 o'clock or few minutes past 3. Should we continue, or do you have any other lectures, or do we have cut exams? So what's your opinion? Maybe I can go about 10 or 20, 15 minutes and finish it. Or if you have other lectures coming up, I don't want to crash into them. Do you have anything coming after 3 or 3:50 around that time? මොකද ටයිම් ටේබල් එකේ 1ට 3 කියලා. කියන 3. මට තව විනාඩි 15ක් වගේ ගත්තොත් තව ටිකක් කවර් කරන්න පුළුවනි. හැබැයි ඕගොල්ලන්ගේ ඔපිනියන් එක මත තමයි ඒක රඳා පවතින්නේ. ඕගොල්ලන්ගේ අදහස් දැක්වීම මත. කියන්නකො මොකද කරන්න ඕගොල්ලන්ගේ අදහස. තව විනාඩි 15ක් විතර කරමු කියන අය අත උස්සන්න, කරන්න බෑ කියන අය කතරේ දාන්නකො. තුනයි. අනිත් පැත්තට කවුරුවත් නැහැ. අනිත් තමයි ටික නිදිද එතකොට? දැන් මෙතන 39ක් ඉන්නවා. 29ක් ඉන්නවා, 3 දෙනෙක් අත ඉස්සුවා. අනිත් කට්ටිය නැද්ද? 4 5යි. නිදිම නැහැ නේද? තව දෙන්නෙක් හැරුණා. හරි හරි එහෙනම් කරමුකෝ. Right. So we have a transistor. I said it can be used to process signals. There are two different ways you can use a transistor. They are called the operating modes. One mode is it can be used as a switch. That means on and off. Another one is it can be used as an amplifier. Right? So that means it can multiply a signal by a certain factor. On and off means only two states. Amplifier means it's a continuous stage. Right? So those are the two operating modes. We will discuss these modes in separate ways. Now we have learned about hydroanalogy. That means thinking of the flow of charge as a flow of water. That gives a certain gut feeling about how things are operating. So now we are going to use the same scenario, same analogy to explain the transistor. Now I believe you have seen taps, right? Water tap. Tap දැකලා තියෙනවනේ, ගෙවල්ලා තියෙනවනේ. How many of you have seen water taps? Tap එකක් එහෙම දැකපුවා ඉන්නවනේ. නැද්ද? Yes? No? Maybe? Okay, I believe you have seen taps, right? So there are different ways, different status that tap can have. Either it can be closed, so the water doesn't come out from the tap. Or it can be fully open, so the water freely flows across the tap. Or it can be in the middle. You have partially opened the tap. Not fully closed, not fully open, only partway through. So water flows through it, but in a controlled manner. The amount of water flowing will depend on how much you have opened the tap. Transistor is similar. If you are using it in an on-off mode, that means either tap is fully open or tap is fully closed. Either current is moving through the transistor freely or it is not flowing at all. When you are opening the tap halfway through, that is similar to having a transistor in the amplifier mode. So there is a certain amount of current flowing, but that depends on the how much you have opened the tap. So that is the second operating mode. So let me show it using this particular example. So the difference is in that this case is instead of tap, you can think of it like this kind of valve, right? So you don't manually open the valve up or down. Instead, you use another flow of water to push the valve up and down, right? So you can see there's a large amount of water going through this valve. But it can be controlled using this small amount of water coming to this space, right? By this small amount of water pressure, you can move this valve up and down. So that will allow flow of large amount of water. So you can control this large volume of water body using a small amount of water pressure. Similar thing is applicable for a transistor. You have a large amount of potential difference across collector and emitter. However, current can't go through it without the permission of the base. So base is like the valve. So depending on how much current you are going to push to the base, this collector to emitter current flow will be changed. So larger base current means larger current flow from collector to emitter. Smaller base current means smaller current flow from collector to emitter. So that is the water analogy for the transistor, right? So you put more current goes through this one. You put less current go through this one. If you don't put anything, or if you put it in a cutoff mode, we call it as cutoff mode, current doesn't flow through this one. If you put it to saturated mode, that means you have fully opened the valve. Then the full current will go through it. In the middle, you have what is known as a linear mode. It's partially open. So the flow of this main current depends on the flow of this current, right? So that is the analogy. So this is the same thing, but now described using a table. There are 4 different modes, but forget about the 4th one. I will not cover that one. Reverse active is not in the syllabus. I put it here just so it will be complete. So when I ask for the exam, say 3. Okay. In the first case, now remember in the NPN case, collector is always have a higher voltage than the emitter. That's a given case. Collector will always have a higher voltage than the emitter. Only the base voltage will determine the different modes. So if we'll start with here, the last one. If the base voltage is less than the collector and the emitter, you are in the cutoff mode. That means no current goes through the transistor. Base emitter is reverse bias, base collector is reverse bias. Both junction are reverse bias, current doesn't flow through it. If you gradually increase the gradually increase the voltage of the base, next you come to this point, the first line, right? Not to this one, this point. Now the base voltage is larger than emitter voltage, but it is less than the collector voltage. Base is somewhere in the middle. Less than collector, higher than emitter. So this is forward bias. This one is reverse bias. Now you are in the forward active mode. This is the linear mode, amplifying mode. You increase the base voltage further. Now it is higher than both the collector and the emitter. So the both junctions are forward bias, and this is known as the saturation mode, the fully open mode, right? So that is how the different voltages and modes are connected. Right? You need to know about this particular table. This is the lowest one, cutoff, then come to the linear or the forward active, then come to the saturation. This is for the NPN. You can have a similar table for the PNP here. I only explain about the NPN. The PNP one is the same, similar, right? Okay, let me see. Okay, you can quickly go through this one. So this is part of the practical. So I'm not going to cover much. So the idea is, if you want to measure how the transistor behaves, you have to measure certain things like this, just like the diode characteristic. You have to measure the voltage and the current. You put this transistor under different conditions and try to measure the current and voltage. So you need to measure the input current and the input voltage. Now remember, this is for a common emitter mode. For other modes, you have different characteristic curve. This is for the common emitter one. So input current is this one. Input voltage is the base voltage. And we take the output from here, right? Collector. So the output current will be the collector current. Output voltage will be the collector voltage. That is clear, right? Because it is in the common emitter. ඒක පැහැදිලි නේද? Common emitter mode එකේ signal එක දෙන්න අපි base එකටනේ. Output එක ගන්නේ collector එකෙන්නේ. එතකොට input current එක මනිනවා කියන්නේ base current එක. Input voltage එක base voltage එක. Output current කියන output collector current එක, output voltage කියන collector voltage එක. That is clear, right? පැහැදිලි නේද?
Yes, sir.
Right. So this is the normal setup for this measurement. You can see you have the ammeters, voltmeters connected like this, and you can change the voltage. That is how you get the characteristic. But now you have a different scenario than the diode, a little bit complicated one, because you have the output side and you have the input side. So you have to check what's happening in the output side separately and what's happening in the input side. What will happen if you change the input voltage to the input current? That is known as the input characteristic. You are changing the input voltage and looking at what's happening to the input current. So that is what this graph is. Input voltage means VBE, base voltage with respect to the emitter, because emitter is the other input terminal. And this is the input current, IB. So you can see it's quite similar to diode curve, right? You have kind of like a knee here. Up to that point, no current, then it suddenly increases. So this is the input characteristic. There can be small changes depending on the output as well, but usually you have the same shape. Now let's look at the output characteristic. Now this might come a little bit complicated when you first see it. So let me quickly draw it in a new piece of paper. Now, if you are measuring output characteristic of a common emitter mode transistor, what are the axes I should have? What should I change? I need to change the output voltage and measure the output current, right? So which terminals gives me the output current? This is the output current. This should be the output voltage. Which terminals gives me the output current? Is it base, collector, or emitter in this configuration? Remember, this is input, this is output. So the emitter is common. So input comes here, output is taken from these two terminals, but this is a common one, right? So output is actually going from here, collector. So output current is IC. Output voltage is this voltage. What is this voltage? Collector
VCE.
voltage. Yes, respect to the emitter, VCE. Right. So this is similar to, if we look at this analogy, you can assume this as collector and emitter, and you have this base controlling line. Okay. So what will happen if the base? So what we are doing is we are basically changing the pressure here, right? Because we are trying to measure the collector emitter current flow and collector emitter pressure potential difference. In the water analogy, it will be the amount of water flow and the water pressure difference. So if this valve is closed, will increase in this pressure produce any flow of water in this direction? Valve is closed, you are increasing the pressure. What's going to happen?
There is no current.
There's no current. There's no flow of water. Similarly, if the base is low, you might have a small leakage current, but nothing considerable. Almost like a flat line. You apply small base current. That means the valve is slightly open. Now what's going to happen? Valve is slightly open. Tap එක චුට්ටක් කරනවා. Pressure එක බිඳුව වුණොත් tap එක හරියට වැඩක් තියනවද? Right? Assuming your water tank is at the ground level, does it make any difference whether the tap is open or not? If the water pressure is 0, වැඩක් තියනවද?
නෑ වැඩක් නෑ.
වැඩක් නෑ. Current එක යන්නේ. Similarly, if the collector and emitter voltage is less, let's say 0, it doesn't matter about the base, there will be no current. but then you gradually increase the water pressure here. Now what's going to happen? Then ටික අපි water pressure එක වැඩි කරනවා. දැන් මොකද වෙන්නේ? මෙතන යන වතුර ටිකට. මුලින් ගියේ නැහැ. දැන් මොකද වෙන්නේ? ටැප් එක චුට්ටක් කරලා
යන ධාරාව වැඩි වෙනවා.
අන්න හරි. ටැප් එක චුට්ටක් කරලා අපි water pressure එක වැඩි කරනකොට වතුර ටික ටික වැඩි වෙනවා නේ. Right. It gradually increases. But can this increase indefinitely? Can the water start to flow indefinitely? ඒක දිගටම වැඩි වෙන්න පුළුවන්ද? Tap එක තාම චුට්ටයි අරලා තියෙන, right? Remember, we have only opened the tap slightly. So can the water be, can you get a very high flow of water here if the tap is only slightly open?
No.
No. So after a certain point, you hit this limit. Tap is only partially open. So then you start to saturate like this. After a certain point, it doesn't matter how much you are trying to push the water because tap is only partially closed, partially open. So this one limits it. Let's say you are increasing the current further, or otherwise you are opening the tap a little bit further. And again, it's starting from zero pressure. ආයි පාරක් කරන ටැප් එක කලින්ට වඩා දැන් අරලා භාගයක් විතර අරලා තියෙන water pressure එක බිඳුවයි. එතකොට මොකද වෙන්නේ? current එක වතුර යනවද? ටැප් එක භාගයට ඇරලා හැබැයි වතුර pressure එක නැහැ. ඊට පස්සේ ටික ටික අපි water pressure එක වැඩි කරනවා, right? Now we are again increasing the water pressure. Now what's going to happen? Will it increase or not? What's going to happen?
It is increase.
It is increasing. Right. Will it increase above this line or less than line or equal to this line? කලින්ට වඩා ටැප් එක අරලා.
Above this line.
Above this line. But again, after a certain point, you are going to hit this limitation and you are going to saturate. So you can do it for different amount of open levels, right? So when it comes to electrical terms, electronic terms, you can say these are the different base currents. So that means how much the valve is open. And this is the collector emitter voltage or the water pressure. This is the amount of current going through it or the amount of water going through it, right? So initially, if the tap is closed, no use. But after that, you can gradually open it and you can see a pattern like this. So for the same pressure, what you can say, let's say I keep the pressure same, and now I'm gradually increasing the base current. In other words, your tank is fixed. You are gradually opening the valve or the tap. Now what's going to happen? Amount of water flow is proportional to the amount you open. Okay. If the pressure is constant, the amount of water flow will be proportional to the amount you have opened the tap. Similarly, if you keep the VCE fixed, your output current, this IC, you can see similar to the proportional to the IB. When the IB increases, IC also increases. Now remember, IB is usually measured in microamperes. This might be in milliamperes. So you change from 10 microampere to 20 microampere, your output might change from 5 milliampere to 10 milliamperes. So this is why it is called an active element. This is why it's able to amplify the signals. You are supplying only 10 microamperes, but it's able to control around 5 milliampere signal. Right? So this is the output characteristic. So it's basically a single, you are basically measuring the output characteristic for different input values and plotting it in the same graph. So this is what the output characteristic is. So we have different names. So this region where everything is closed is called the cutoff region. This region where everything is fully opened is called the saturated region. And this region where output is proportional to the input is called the linear region or the active region. Right? So those are the three regions in our output characteristic graph. I will do the last one and finish it because I think I'm already running a little bit late. But you need to know about the calculations as well, okay? Other one is called the transfer characteristic. So the transfer characteristic basically maps the input and the output together. So far we have looked at the input as a separate graph, output as a separate graph, but we have not looked at how the output change with the input. In the input characteristic, we look at what happened to the input current when the input voltage changes. in the output characteristic graph, we had look at what happened to the output current when the output voltage changes. Of course, we had look at different cases, like different IPs, but the main axis represent those. Now we are looking at what happened to the output when you change the input. So there are two different ways you can look at it. Either you can measure the input current and output current, or you can measure the input voltage and the output voltage. So those are the two things that you are seeing here. These are known as transistor characteristics, sorry, transfer characteristics. So this is the base current and the collector current. You can see it's fairly a linear relationship. And here you can see the input voltage and the output voltage. Now remember, this is an inverse kind of relationship. Why? When the valve is closed, the pressure difference between the input and output will be the highest, right? Valve එක වැහුවම තමයි උඩ යට pressure එක වැඩිම වෙන්නේ. Valve එක full ඇරියොත් එහෙනම් මෙතන pressure difference එකක් හිටින්නේ නැහැ වතුර free ගානගෙන යන හින්දා, right? So similarly, when you are saturated, the pressure is very low. The potential difference is low. That means VC is very low. But when you are at the cutoff region, there's no current flowing through it. It's like an open switch. So the potential difference is very high across these two terminals. Right? That's why you have this kind of curve as the transfer characteristic. You need to know about these equations. So these are very fairly straightforward equations. Let me very quickly tell you how to do this kind of calculation. Usually in the common emitter configuration, if it is in the linear region, most of your questions will be in the linear region. You can assume the potential difference is equal to the VBE. So if it's a silicon transistor, you can probably have 0.7 VBE here. So that is what measured by here. Beta means the current gain. That means in the common emitter configurations, collector current divided by the base current. Collector current divided by the base current. So in this calculation, beta is given as 100. So whatever the base current here, 100 times will flow through the collector current. So that is the idea. So the first one, find the currents IB and IC. Right. Let's draw the question. Now we have a transistor, a 6 volt here. It's an NPN transistor. So we have the ground line here. We have a resistor also here. 6 volt, 2 kilo ohm. Okay, so we have 2 kilo ohms here, and this one has 503. I don't know, let's say 500 kilo. It's 503. I don't know. We'll keep it 503 then. And it says beta is 100. PBE is 0.7 volts. That means this has 0.7 volt. So this is 0 volt because this is the ground line. So what is the voltage here? මෙතන voltage එක කීයක් වෙන්න ඕනද? මේක 0.7ක් වෙනස් නම් මෙතන බිඳුව නම් මෙතන කීයද?
0.7යි.
Yes, 0.7 volt. Now remember, this one is 6 volt. 6 volt power rail. This one is 0.7. So what is the current through this resistor? You can
I-
calculate the current through this one. I equals V divided by R. V is 6 minus 0.7 divided by 503. I think it should be 530. That's a small mistake. Then you can subtract it, right? You get 5.3 volt here and 530 here. This will be the current through this one. So once you know the IB, so this current has to go through the base. There's no other path. This is the only line connecting this one. It has to go through the base. So once you know the base current, you can calculate the collector current. How can you calculate the collector current? Beta. Now remember, beta means IC divided by IB. So IB we have already found. So if we know the IB, we can put it here. So multiply this by 100, you get the IC. Right? Beta means IC divided by IB. It's given in as 100 in the question. So that means collector current is 100 times larger than the base current. We have found the base current, multiply by the 100, we get the collector current. So now we know the IC as well. IC, we identified. So the question is asking, find the voltage across RC. Voltage across this one. So if we know this current, we can find the voltage. Why? We can again apply V equals IR. V is the one we want to find. I is the current, 5.3 into 530 multiplied by 100. So this is IC, right? This is IB, this is beta, this is IC. R is 2 kilowatt. So this will be the VRC, voltage across the RC connector. Next one asks, find the VCE. How do you find the VCE? Now we know the voltage from here to here. We know the voltage from here to here. So the difference is here, right? From here to here, you will get this voltage. From here to here, you have 6 volts. So in between, you have this voltage. So the difference will be, VCE will be 6 volt minus whatever the voltage here. Right? So that is how you do the transistor questions. Most of them will be in the same kind of scenario. You have these kind of terms, IB, IC, RC, and things like that. So start with what you know. Usually you are able to start from one end and gradually move along that line and get the results. Right. I think that should be sufficient for today. So if you have any questions, please either you can ask me now or you can ask later or email me. But please go through the transistor calculations. Okay, because we will ask questions from transistor calculations. So go through them. You can look at a much more detailed video in the LMS. There's a link for the previous year's videos. So it's the same syllabus, same textbook. So it will match exactly for you. So go through those videos and you should be fine. Right. With that, I'm going to wind up for today's lecture. Anything you want to ask?